and that is this idea of self-inductance. Now, that's not what it says up there. It says mutual inductance. I'm going to ease into this idea of self-inductance with an in-between step. Let's talk about the mutual inductance between two coils. Now, if I have these two coils, one hooked up to an ammeter and one that I can hook up to a battery, if I change the current in this coil, I'm going to induce a current in that coil. Let's call this the primary, the secondary. Can you see that induced current there? Just barely. It's just barely moving. Now, how could I make that induced current bigger, stronger? Yeah, put these closer together. And now, I get a bigger induced current. What I say is that these two coils are now more closely coupled. The field lines, when I connect this to the battery, it becomes an electromagnet. The field lines spread out like any magnet. And when they're far apart, those field lines, not very many of them make it through the secondary coil. But when they're right up next to each other, all the field lines generated by the primary go through the secondary. And that's why I get a bigger effect. Now, if I take this bar of iron and put it between the two, that magnifies the effect greatly. You see that over there? What's happening is, as I connect to the battery, this becomes an electromagnet. That then magnetizes this iron rod, and that sends field lines, extra field lines, through that secondary coil. Okay? So if I want to really have the magnetic field in this coil connected to the magnetic field in that coil, I want them close together, and I want the space in between filled with iron. Now you can see that even if they're far away, if I've got the iron rod, they're still pretty strongly connected, because the iron rod is being magnetized, and that's sending field lines over there. Now here's the idea. I can say that the number of field lines through the secondary coil is proportional to the current that flows through the primary coil. Okay? Now, whenever I have a proportionality, I can replace that with an equal sign if I put in a constant of proportionality. This constant is what we call the mutual inductance. And you can see what it means by setting this I equal to 1 amp. If this is 1, then M is equal to the flux. So that gives me an idea of what it means. For every 1 amp that I send through this coil, my mutual inductance tells me how many field lines go through the secondary coil. And I can make that M, that mutual inductance, bigger by putting the coils closer together and filling the space with iron. Okay? Now, if I use Faraday's law, that tells me that there's an invisible battery set up in that secondary coil that, if I use this principle here, depends on how quickly I change the current through the primary. Okay? The quicker I change the current through the primary, the bigger the battery that I set up in the secondary. Now you see this idea of mutual inductance a lot in transformers. Transformers will not be on the final exam, but you've experienced them in everyday life. You know that they're up on the top of telephone poles, and that every now and again they blow up, right? And when they blow up, your house is dark for a while. Well, a transformer is just two coils that are connected by an iron donut. You got essentially an iron donut with a coil on the left side and a coil on the right side. and we use these transformers to change the voltage. It turns out that when you're moving current across, say, a desert, you lose a lot of your power. Twinkle, twinkle, little star, power equals I squared R. And so the bigger the current, the more you're losing that power. And so they find that if they send that power across at very high voltage, they don't need very high current to get the same power. And so they send it across at tens of thousands of volts. Now you don't want tens of thousands of volts near your children or your pets. And so before it gets to your house, we step that down to 120. And we do that with a transformer. It turns out that if you have two coils on an iron donut, and one of the coils has twice the turns, you're going to change the voltage by a factor of 2. The one with the smaller number of turns is going to have half the voltage and twice the current. And so that's how we essentially step voltage up and down. Now, that's not going to be on the final exam. That is, yes, sir?
So what causes them to explode?
What causes them to explode is a force that turns out that there's an energy density inside there that is given by V squared over 2 mu naught. And the bigger the V, the bigger the energy inside there, and it's just a containment issue. I was working at Lawrence Livermore Labs, where I was working on the supercomputers. They have the biggest supercomputer center there, or had, and there you would bid for time. You would say how many minutes you had that you needed for your run. Say, I need 10 minutes. And then you would tell them how many minutes you would pay for. And the time would go to the highest bidder. And that's how people would get their jobs done. They just, if they had a grant, they'd say, I want 2 minutes and I'll pay for 10. And so I didn't have much money, so I was always running at very low priority. I was always the last person to get any computer time. One night at 2 in the morning, I was working in my office, and everything went dark. One of the transformers in the lab just blew. There was a great big huge bang. So rather than going home and calling it a night, I stayed, and at 4 o'clock, they got things back online. But everyone else had gone home. And I went into that supercomputer list of who was on it, and I was the only one. And I said, give me 100 minutes, and I'll pay you a penny. My job ran all night long. I got like 4 months of work done that one time. Anyway, that's not going to be on the test either. Now, we have a little pretest here. This is simple, simple, simple. You'll be able to do it in your head. It's just going to get you thinking in the right direction. Very simple. The battery current leaves the positive terminal of the battery and goes around clockwise. To find the induced current, I use the fact that field lines, external field lines, are coming out of the North Pole and going down through that loop. So I have an initial flux down, and as the magnet gets closer, it gets bigger. That gives me a change in flux that is down. I fight that change with an induced flux up. Now, in order to have induced flux up, use the right thumb to represent that flux. The induced current has to go counterclockwise. Now, if I think of the total current as the sum of those two, my induced current has reduced the current through the resistor. But what if I had pushed a south pole down on that circuit. In that case, the induced current would be in the same direction as the battery current, and it would help the battery current. Now, in this case, I can either hurt or help the battery current with this induced invisible battery. It depends on how I bring that magnet down. We have things called inductors, where we also find that the induced current fights the real current and sometimes helps the real current. And we have to keep those two ideas, the two currents, separate in our mind. Now, an inductor is just a coil of wire. And when we draw it on a schematic, we usually separate it out into two elements. We realize that this 3 miles of wire has certain resistance, and so we represent that as a resistor. And then the fact that it's coiled, we represent with this symbol here, and it's measured, its inductance is measured in henries. We'll talk about that in a moment. Now folks, before we go any further, let me just point out that in all of analog electronics, there's only 4 things we deal with: resistors, capacitors, inductors, and batteries. That's it. So this is not some obscure, gee, why do we have to deal with it before the final? This is the 4th piece of 4. Okay? Now, what we find is that that coil is going to fight a change in flux through the coil. Now, up until now, I've been telling you that there's 2 flavors of flux. That there's external flux and induced flux. And I did that because that was going to help you learn Lenz's law. But I was lying to you. That coil can't tell the difference between external flux and induced flux. It just flux. And all it knows is that it doesn't like a change of flux through its own coil. Whether it's from someone else, like a magnet, or whether it's due to its own magnetic field. Okay, and we're going to find that that has very important effects on a circuit. What I can say is that the number of field lines that pass through a single coil depend on how much current is in that coil. It's proportional. If I double the current through this coil, I double the number of field lines. I replace that proportionality with a equal sign. I put in a constant of proportionality, and that constant of proportionality we call self-inductance. That's where we were headed. Now you can understand what self-inductance is, again, by setting I equal to 1 amp. Self-inductance is how many field lines go through this coil for every 1 amp that's going around the coil. How can I make that self-inductance bigger? Well, I can make more turns in the coil, or I could fill up the space inside the coil with iron, and that would give me more field lines for every 1 amp. Now, here's what that does to Faraday's law. I get an EMF in a single coil when I try to change the current through that coil. And the bigger the self-inductance, the bigger the invisible battery that will fight that change. Now, what this means is, a coil will always fight the change in its own current. Now, you've seen this in everyday life, I think. If you've ever unplugged something that has a coil in it, like a waffle iron, for instance. You unplug a waffle iron and you get a great big spark. Why is that? Well, inside a waffle iron you've got heating coils. But coils are coils. And any coil is going to fight a change in the current through it. And if you're unplugging it, you're trying to change the current from something to nothing. It will fight that change. It fights by sending a spark. Okay? Now, if I try to take the current through a coil from 0 to some final value, say 4 amps, if I try to take it instantly, what does this formula give me for my invisible battery to fight that change? Delta I is going to be 4 minus 0, that's 4, divided by a delta T of 0. Plug that into your calculator. 4 divided by 0. What happens? Yeah, your calculator explodes. There's shrapnel all over. People get hurt. Okay? You don't do that. Okay? What that means is that if you try to force this to be instant, an invisible battery will rise up that can be as large as it needs to be to fight that change. Okay? As large as it needs to be. Now, what happens in practice is that instead of jumping up to 4 amps, you've got to gradually ramp up to 4 amps. It takes time to get there. And the bigger the self-inductance, the longer it's going to take to get there. If I look at right here where I close the switch, right before I close the switch and right after I close the switch, can't be very different. I can't change that current instantly. I've got to gradually ramp it up. Likewise, if I want to turn current off, if I want to take it from 4 amps down to 0, I can't just drop it down to 0. I've got to gradually ramp it off. That's what that spark was when you unplugged the waffle line. Now here's a bigger spark. Watch that again. I showed you that little clip before when we were talking about V equals IR. But now we can talk about why the V was so big. What they were trying to do is disconnect a city from the power station. Well, that city had all sorts of transformers in it, all sorts of coils, all sorts of self-inductance. And all of those coils did not want to change their current from something down to nothing instantly. And so when they broke the line, when they forced it to be disconnected, it said, no way. You got to gradually ramp us down. And that was a big enough invisible battery to throw a spark meters. Remember, it takes 30,000 volts to throw a spark a centimeter. That's many tens of millions of volts that is generated to fight that change in current.